Hello, welcome back. This is notes 2D on ionic bonds. This is notes 1 of 2, so there'll be a second set of notes today on covalent bonds. So don't think you're done when you're done with this video. I just filmed it as 2 so that you can take a break in between. The first thing that you need to do, just like the start of all of my notes ever, is the quick review. So I want you to pause. You're going to use the word bank down here at the bottom to fill in the blanks on the quick review, and then unpause when you're ready to check it. All right, you've got them all filled in. You're ready to go? Now I'm going to give you the answers. For a chemical equation to be balanced, there have to be equal numbers of atoms on each side, of each element on each side of the equation. The reactants are on the left, and the products are on the right. You tell what elements are involved in an equation by looking at the letters and using the periodic table. You tell how many atoms are involved by looking at the numbers, which are called subscripts because they are under the letter script. All right, pause and make sure you get those written down, and then we can move on. Now I'm going to go ahead and delete it. I do want to point out one thing to you before I keep going. You'll notice that some of the notes are highlighted. If it's highlighted, that means it's guaranteed to be on the quiz and therefore on the test. So it's a whoop, whoop, test question alert. It's a TQA if it's highlighted. So anything that's highlighted on here, that means it's guaranteed to be a question on the quiz or on the test. All right, so normally it's the book fair during this time of year when I'm talking about this. So I bring this up as something to think about because you're already thinking about the book fair. I don't think there's a book fair going on right now, so I don't have to do my usual caveats of this isn't real and all that stuff and that I make stuff up. So, but still. All right, so we're going to pretend that we've got the book fair going on and that you and your little brother both want to go. You both want to buy something that costs $7.50, but your mom only has $15. She's got a 10 and a 5. So she gives you the 10 and she gives your little brother the 5. Well, what are you going to do? How are you going to get what you want to get? Well, see, here's the thing. Both you and your brother want to go buy the item for yourselves. So you can't do the whole one person takes all the money and goes and buys both things. That's not going to work. You want to go shopping and buy for you. Your brother wants to go shopping and buy for him. So what can you do? There we go. That's a good idea. So what we're going to have to do is some kind of something where I go with my $10, I buy my item, I take the change and either leave it with the librarian with my little brother's name on it or take it down to my little brother's classroom and give it to him so that he can then go and buy his item. All right, put that in your own words on this line right here. Something about how one of you had a little extra than you needed and you were able to give the extra to the one who didn't have quite enough. That's what we need to sum up in this little section right here. So something basically like that can happen between atoms, and it's what happens in ionic bonds. So your little brother has $5 and he needs $7.50. So he's just a little short of what he needs. So anything that has 5, 6, or 7 outermost electrons, what's the vocabulary word for that? Those outermost electrons are the, good job, valence electrons. The valence electrons are those outermost electrons. And with 5, 6, or 7, we almost have enough to be a stable 8, but not quite. Then an atom with 1, 2, or 3 valence electrons, so something from the left-hand side of the periodic table, a metal can easily lose them. So they just get rid. So just like me with my $10 and I had extra, I have extra to give away so that I can make other people have what they want. That's what happens in ionic bonds. So when atoms have more than 4 valence electrons, so something from the right-hand side of the periodic table, a non-metal, they can lose them. They can give them away to other atoms. They can lose them so that other atoms, which have more than 4 valence electrons, can become stable. So it's almost like, oh, well, I don't need these extras. They're actually making me unstable. So if I get rid of these extras, I'll be doing much better off. So what am I talking about here? Well, everything in family 1, 2, and 13. So we've got those transition metals in the middle, but the alkali metals, the alkali earth metals, and then family 13. That has 1 valence electron. They all have 2. They all have 3 valence electrons. All of those are very much willing to get rid of those ones on the outer level so they can be stable. I think of the alkali metals, the ones in family 1. I think of those like it's the party that everybody that you wanted to be there is there, but then your mom also made you invite the weird kid from next door that you don't like. So everybody's there that you want to be there, but that one extra person is really making you upset. Maybe your mom made you invite that aunt that always squeezes your cheeks and makes you feel really embarrassed and tells stories about when you, I don't know, ran around naked when you were a kid. You don't want that person at the party. You will do anything to get rid of that extra person at the party. So these ones in family 1, they will do anything. That's why they're so unstable, right? That's why they're so highly aggressively reactive. This is the periodic table. Noble gases stable. Halogens and alkalis react aggressively. The reason why alkalis react aggressively is they have that one extra. And just like you at the party who don't want that weird kid over there or don't want that aunt telling stories about you over there, you're like, Mom, please make her go away. And once she's gone, you're like, okay, whew, I'm happy now. I'm good. That's what happens with things in family 1. They get rid of that one and they're now stable and happy. So in this way, atoms either gain or lose electrons. And now we no longer have a neutral atom. We now have ions. They do become more stable, but we now have a charge. So, for example, we've got our sodium ion. Sodium has 11 protons in its nucleus and then 11 neutrons in its outer ring. 2 here, 8 here, and then 1 here. But look what happens to this 1. It jumps over and fills in, where chlorine has 17 protons. So it has 7 in this outer energy level and just needs 1. So the folks that are in the halogens react aggressively. They're Mr. Steal Your Girl. Halogens need that extra electron so badly, they'll go get it. They'll literally like go. So it's the party where everybody is there that you want to be there except your crush or your best friend, or however you want to think about it. That one person that you really wanted to be there isn't there. And it makes you mad and you're angry and you're volatile. And until that one person gets there, you're just not going to be happy. And that's what they do. These halogens will go out and grab an electron violently, aggressively. Mr. Steal Your Girl. They will go and grab your girl if they want it because that's what makes them happy and stable. Fortunately, sodium is like, go ahead, take her. I don't want her. She annoys me. So it works out, right? Okay, so this one now has 8 in its outer energy level because it lost that extra 1. This one now has 8 in its outer energy level because it gained 1 and everybody's happy. So in this way, sodium now has 1 fewer negative charges than it had positive charges. So it now has a positive charge. It has 11 protons, but only 10 electrons. So it has a positive charge. The chlorine gained an electron. So it has 17 protons, but it has 18 electrons. So it is now has a negative charge. And we know that positives and negatives attract, opposites attract. So those two snap together and we get a NaCl, a salt molecule. Here we've got lithium because we've got 1, 2, 3. But that 1 jumps over to here. This is fluorine because we've got 9, but now we've got 10 with that extra 1. So lithium fluoride, the lithium ion is positively charged, the fluorine ion is negatively charged, and they snap together to make lithium fluoride, which is a type of salt. So vocabulary word, obviously, since it's highlighted, this is something you've got to know. An ion is an atom or group of atoms that has become electrically charged. So when an atom loses an electron, it loses a negative charge, so it becomes positive. When it gains an electron, it gains a negative charge, so it becomes a negative ion. So when the sodium lost one, it became positive. When the chlorine gained one, it became negative. So here we have sodium with one valence electron. It jumps over here to the chlorine. So sodium has 1, chlorine has 7. But now when this 1 jumps over here, it now has 8. So the sodium's VE is transferred to the chlorine. The transfer changes both atoms into ions. They're now no longer considered to be just atoms. They're now ions. The sodium ion becomes a positive ion because it lost an electron, and the chlorine becomes a negative ion because it gained an electron. Negative and positive attract, just like magnets. So when the charged ions come together, we get NaCl. And the positive and the negative balance each other out. So NaCl itself is neutral. It's electrically neutral. So what are we talking about today? Ionic bonds. So an ionic bond is the attraction between two oppositely charged ions. I want you to think about it the way you think about magnets. So we said that ionic bonds were kind of like magnets. So I've got some magnets here that I want to look at. So we're going to pretend that this is hydrochloric acid and this is sodium hydroxide, and we're mushing the two together and creating that neutralization reaction. And we're going to have water molecules, but then we're also going to have some positive sodium ions and some negative chlorine ions that get separated and are floating around in the water. And so I want you to pretend that the space in between each of these magnets is water molecules. So any place that you see black table, it's actually supposed to be a water molecule that's there. All right, so these are sodium, positive sodium and negative chlorine ions that we created. We separated out because we mixed together hydrochloric acid and sodium hydroxide, and they neutralized each other, and they made water, and then they made all these ions. We've got all these positive sodium and negative chlorine ions floating around in the water. Now, obviously, that's where I need to stop. So as the water starts to evaporate, that means that the space between these positive hydrogens and negative chlorines is becoming smaller. And so as that space goes away, eventually, because one's positively charged and one's negatively charged, they snap together. And so now we have salt water. That wasn't supposed to happen just yet. That is technically what happens, but I don't want it to happen just yet. Okay, seriously, this is getting silly. So now we have our salt molecules. Our positive sodium and our negative chlorine have snapped together because the water between them has evaporated away, and we've ended up with all of these salt molecules floating in the water. But the water continues to evaporate away. And as it does, because the positive side of the sodium is still attractive and the negative side of the chlorine is still attractive, we now get these lines of salt molecules that have all stuck together. And then the water continues to evaporate and they continue to be brought closer together. And we end up with it connecting into longer strands, and then it's also attractive on all four sides. So now we start to get sheets of salt crystals being formed. And then eventually, because it's still attractive on all four sides, it's also attractive on the top and bottom, they end up sticking together like that. And of course, we would get a much prettier crystal from actual ions, but we then get a salt crystal that's left down in the bottom of our glass of water. So all the water has evaporated away and all the salt has clicked together into a nice little salt crystal. So that was fun. This attraction is similar to the opposite poles of two magnets, just like we showed. So when the two ions come together, the opposite charges cancel out. So every sodium ion has a positive 1, is balanced by the negative 1 charge for the chloride. So the formula for sodium chloride, table salt, NaCl, shows you this 1-to-1 ratio, that I need 1 positive Na sodium for every 1 negative Cl chlorine. And that's why the formula is NaCl with no subscripts, because they balance each other out without needing any extras of anything. Compounds are electrically neutral. So when ions come together, they do so in a way that balances out the charges of the ions. So that means that you can predict what the chemical formula is going to be for something. If you know how many valence electrons something has, you can think about what the charge would be for that ion and then make a prediction on what the formula would be. There are some ions that are made from more than one atom. These are called polyatomic ions. Poly, like polygon, meaning many-sided. Poly just means many, and atomic means atoms. So polyatomic just means many atoms. And it means that the ion is made from more than one atom. We don't just have, for example, hydrogen has a positive charge. When you drop an acid into water, you get those positive hydrogen ions. But when we drop a base, hint, hint, into water, we get those hydroxide ions, which are polyatomic. So what's the polyatomic ion we've already talked about that is produced when bases dissolve in water? OOO, right? OH negative. Hydroxide is a polyatomic ion. Pause it if you need to get that stuff written down, but I'm erasing. So this little chart of ions and their charges is just something to look at. Like I said, you can predict what the formula would be. So we know that sodium and chlorine both have 1, so they balance each other out. Potassium has 1, so potassium chloride would be KCl. You don't have to write these down. You can just watch. It's just for the fun of it. You see, magnesium has a charge of 2, and oxygen has a charge of 2. So magnesium oxide would just be MgO. But what do you do when you have different charges? Like sulfate has a negative 2, and maybe I want potassium sulfate. So if I've got a negative or plus 2 here and a negative 2 or a plus 1 here and a negative 2 here, that means I need 2 of these to balance it out. So K2S would be potassium sulfate. So carbonate has a charge of 2. So if I want calcium carbonate, calcium is in family 2. It has 2 valence electrons. Carbonate has 2 as a negative. So calcium carbonate would be CaCO3 because carbonate itself is CO3. You don't really have to know any of those for the test. You can see it's not highlighted, but I did want to talk about it. So where do chemical names come from? In ionic compounds, the name of the positive ion comes first, then followed by the name of the negative ion. Usually, the name of the positive ion is the name of a metal most of the time, except for when it's hydrogen. When it's hydrogen, that's not a metal, but most of the time it's going to be a metal. Potassium, calcium, sodium, those are all metals. They're all from the left-hand side of the periodic table. If the negative ion is an element, you change the end of the name to IDE. So I know y'all have wondered, how in the world does she know what that is? Just look at that and say that that's ferrous oxide. Well, I know that Fe, ferrum, is iron, and I know that O3 is oxygen, so ferrous oxide. I know that becomes IDE just because of this rule right here. So MgO is magnesium oxide. If the negative ion is a polyatomic ion, you just leave it alone. So calcium carbonate. Calcium carbonate is just calcium carbonate. You don't have to do anything fancy to the name. You just have to name the ion that you've got. All right, again, if you need to pause that, please do. I'm going to move on. All right, finally, we have the properties of ionic compounds. And these right here are definitely a TQA. You need to know the 3 things that make ionic compounds special. So one thing is that they have a 3-dimensional crystal shape. They've got a 3D crystal shape. So they have an orderly 3-dimensional arrangement. And we get this pattern that's created by bonding on all sides. So you get, I did that on purpose. So you get regular, even cubes and crystals from things that are ionic compounds. Ionic compounds have a high melting point, a very, very high melting point. It takes a lot of energy to break apart the strong attraction of that crystal shape. Think about it. I can get salt to dissolve, but can I get it to melt? If I take a pan and put salt in it, it's going to sit there. It's a rock. You could throw salt in a fire and it's not going to melt because it doesn't melt until 801 degrees Celsius. So it doesn't go from a solid to a liquid until 801 degrees Celsius. So you are not going to melt salt just on your stove. It's not going to happen. You're just going to get warm rocks. You're going to get hot salt. And then the last thing is electrical conductivity. So when they are dissolved in water, they can conduct electricity. Now, salt itself, like if you just tried to run electricity through just some salt, it's not going to work. But when you dissolve it in water, when those ions are allowed to be loose in the water, they conduct electricity. Water, pure water, does not conduct electricity. But if we put salt in it, it does. That's why our bodies work, because they are conducting electricity through the salty water that is contained in our bodies. So ionic solids do not conduct electricity. So you can't get electricity to flow through a salt rock, but you can get it to flow through salt water. All right, that's the end of notes 2D. I want you to pause, set your timer for 5 or 10 minutes, take a break, walk around outside, do some jumping jacks, get a sip of water, maybe have a soda or some juice or something, and then come back and do notes 2E. I want you to take a little break in between, okay? All right, now have a lovely day. Well, no, do have a lovely day, but come back after your break. 10-minute break, and then come back to finish up the notes. Bye. See you in a minute.